Okay, welcome to CE 5700, Geotechnical Engineering, Earthquake Engineering. This is lecture 2. We start to talk about the strong earthquake motions. So earthquake motions are mainly characterized by 3 points. First, the intensity of shaking, which kind of like discuss or describe the strength of the earthquake, and also the durations of shaking, which is the length, and very importantly, the third kind of important factors is the frequency content. And the parameter that affect earthquake ground motions are the magnitude, earthquake magnitude, the distance from the fault. So earthquake magnitude and distance, those are the two dominant factors. And in fact, the parameters affecting earthquake go into descending orders in terms of importance. The site conditions are also very important. The fault type, the tectonic settings, we talk about this, whether this is subductions, earthquakes, or other type of like tectonic settings, it matters. The travel path, geology, how deep is it from the earth, and also some special effects like rupture directivities, topography, so forth and so on. And with every new earthquake, specifically like the major earthquake, like the one that happens like last year, 2019, which crest earthquake, our database of recorded ground motions increase. This is especially true that in the past decade, and also with the advance of technology, we have more and more sensors put on the earth, and also the cow, and also the advance in the IT size will help us to record the data more properly. You could imagine like a couple decades ago, so it's not like typical. It's not easy to find earthquake record, but now we're getting more and more. This helps us further understand and predict how these parameters we talk about here affect the strong ground shaking. So the data is very important, and there's a lot of effort in the past for seismologists and geotechnical engineers come together to store to manage the earthquake ground motions database, and this is done by the PER, the Pacific Earthquake Engineering Research Center. They are kind of like Berkeley dominated, but it is very popular in California, and pretty much like UCLA has a lot of influence and also involvement on those projects. So the PER earthquake motions database, which is online, I will put up the link on Canvax, so you guys can go into it. And for practice in California, that's particular important. It's called the NGA RES2 project. So NGA stand for next generations attenuations. We talk about all those attenuations later. And in the past, the very first project is called NGA RES. So that was like started 2 decades ago, and about maybe 5 or 6 years ago, they have a version number 2. So they expand their database with a much better web interface at the PER website. So this project called NGA RES 2. And in between NGA and NGA RES 2, there's another project called NGA East. So the West stands for the West Coast of America. So this describes all the ground motions recorded in the NGA, in the West Coast of America, and the NGA East is for the data, the ground motions collected at the East Coast. So there's a huge difference between like in terms of tectonic settings, and also in terms of geology. There's a huge difference between East Coast and West Coast. East Coast pretty much is kind of like a rock site, a rock dominate geological setting, But West Coast is we have the subductions tectonic settings, and we in some particular area like the Bay Area is features with like a very soft soil deposit. So the earthquake record that we get from west is very different from the east. So when designed for like a project in California, we need to use the NGA west too. We cannot use NGA east. So this class we will focus on NGA west too. And that's like a paper particular I upload on Canvax to discuss about the development of the database NGA REST 2, and for even more detailed documentations on the database and how to use the interface on the PGA websites, you can go to this report too. And your semester project, you will be like heavily involved on using selecting ground motions. I think start with also homework number 2. So this website, the PGA website, we will always come back to it for you to, or you need to spend time. Highly recommend you spend time to learn how to navigate the website and how to obtain earthquake record from this website. So you learn it now, and when you go practice in the future, this is something you need to come back to. And at the end of this lecture, I will give you examples. I'll walk you through how to make use of this website to get the earthquake record you need. So first, intensity. So here on this picture shows you 3 geophones, which is very helpful for which is used to record earthquake ground motions. And this geophones here, you will be set up at orthogonal directions. So this is the vertical. So this kind of like coming in and coming out of the paper. This is the C directions, and this could be your X directions, and this could be on Y directions. And imagine like the propagating of the shear wave. Where earthquake happens, right, is upward propagating shear wave, and imagine this go up through the Z directions. So you can measure this geophones setups can measure ground accelerations in 3 orthogonal directions, and often like the vertical accelerations is less than horizontal accelerations. So that's why like engineers used to put more focus on the record on the X and Y directions of earthquake motions. But each new major earthquake, we learn something new. So we are still humble. We are still very humble that our study in earthquake engineers is relatively very young compared to like the history of the earth. So so whatever like we keep observed in the past, may not be true in the future. So in the 2010 New Zealand Christchurch earthquake, it showed us the vertical accelerations that we caught from the geophones actually indeed is larger than the horizontal ones. And when we like pick up those earthquake ground motions record, we need to be aware that like where do we install those geophones or any like accelerometers, and the locations where all those instrumentations at matters a lot, whether it is at the rock outcrops or on the soil surface. It matters. Because imagine that if your instrumentations is put on a rock outcrop, which means what you get is pretty much is without there's no like a soil effect over there, so that didn't go through the amplifications or de-amplifications. So be very careful on that. But if your geophones or your instrumentations is put on top of soil or buried in the soils, or like you anticipate that, like, when earthquake happens, the upward propagating shear wave. So again, when earthquake happens, you will be kind of like a upward propagating shear wave. So whether this shear wave, if it does it like a travel through the soils matter, because when you enter the soils, it could be amplified or de-amplified, depends on the soil type. So your locations of the instrumentations matters too. So for each records, then we can obtain the if you use accelerometers, then you can obtain the peak ground accelerations, and with the record, then you also can get other parameters that you need. Maybe the peak ground velocity, and also maybe the peak ground displacements. So here is a record of the 3 acceleration time history that we got from geophones. So it has 2 orthogonals, like a record in the horizontal directions. So east, west, and north, south. And also we have vertical measurements. So if you can see here, the vertical record in terms of peak ground accelerations is less than the directions that you get from x and y. So z directions is less than x and y. And this is measurements from the Gilroy earthquakes in California. So now we have the accelerations time history, and if we do our integrations, then we can recover other informations like peak ground, not only the peak ground, but also the time history of velocity and displacements. There was an argument, actually it's more like a development, that people now think velocity may be a better characterizations of earthquake events than accelerations. So that's this discussion is still ongoing, but in the past, maybe last decades, it is predominant. It is dominant that like people would use accelerations for the design. But what I see now, getting to this generations or this decades or within this 5 year, there's more and more research and experimental data so that velocity may be a better parameters than accelerations. And displacement is always useful because it tells you like how much deformations are there. Passes the displacements and accelerations being the important ones, and now you cannot ignore velocity too. So with the record that you obtained from accelerations, if you do the integrations, then you can recover the information from velocity. So some simple techniques that we learned before in the mathematical calculus class. It's like if you integral the accelerations, then you will get the velocity. So since you are getting like discrete data points, digitalized points. So if you use the trapezoidal method, then you can using the approximations. If you have used much smaller delta t time steps, then you will get more accurate results. So with the simple integrations, then numerically we can recover the velocity time history. So for example, here's the same record that we get from the Gilroy site. We focus on one of the horizontal measurements, the east-west record. So if we have the acceleration time history, if we integrate it once, then we will get the velocity time history, and if we integrate it one more times, then we get the displacement time history. So with the displacement time history, then we know how much the ground have moved because of the earthquake. So there's a 2 record, and one is from the rock site and the other is from the soil site. So you will see for this example, for this site, in fact, de-amplifications has happened when the upward shearing wave travel through the soils. In the walk, you got a PGA peak ground accelerations of about 0.4, but after you travel through the soils, it de-amplified it to 0.3. And bear in mind that this is not a must. It always the amplifications to be happens. It depends on the soil type. If you have very stiff soils, you could also have amplifications. But if you have soft soils, you will have de-amplifications. But also bear in mind, it's not de-amplifications is not always like a safe or a good thing to have, because if you look at this, if you do your de-amplifications, very likely what happens is you will slow down the frequency. So for example, if you have your earthquake right there, and if you go through a de-amplifications, you will becomes like maybe a longer amplitudes. That may be the frequency may be changed, and with the change of the frequency contents, you may, if you do after you have done the integrations, you will induce more displacement than before. So for example here, in fact, the peak displacement is larger than what happened in the walk site. So it's always complicated, and you need to look at all the issue. So PGA stands for peak ground accelerations. Some reference in the old days, Professor Seat liked to call it to be AMAX. So by far, this is the most widely used earthquake intensity parameters. It's true in the past, but the earthquake engineering is still like a evolving technology, and who knows, like 10 or 20 years later, people will think there's enough data to prove that velocity is better than accelerations to be the common parameters to describe earthquake intensity. So when we say accelerations, very typically we will express both the single point of peak ground accelerations or the whole earthquake time history to be the in terms of g. So we multiply the whole thing by 9.81 meter per second square, or 32.2 feet per second square. And again, what is a PGA? So PGA is the peak point within an acceleration time history, like here. So it is absolute value of the time history. So no matter is the positive or negative, but it is the peak amplitudes. And peak ground velocity is very similar idea. But now, after you have integrated the acceleration time history once, and the maximum point come with it, independence of the amplitudes, the sign, then the maximum point will be your peak ground velocity, same as the peak ground displacements. After you have integrate your velocity time history once, then you get your displacement time history, and the maximum points is reference to the peak ground displacements. So there's some potential problems on just using one point to represent earthquakes. So we want to represent the intensity of earthquake. The peak point is nice because it tells you the maximum loading amplitudes, but this simple parameters, it has a major shortcomings. Is that if you just pick one point to represent the whole ground motions or loading history, it didn't capture the frequency content, which may also be important because remember, lecture number 1, we talk about the resonant effect. So if you have above ground structure, you know your design buildings, so you know the lateral time period of your 10-story structure, for examples, and if you just use PGA to represent your earthquake loadings, then it's not sufficient to tell you, whether your loading parameter here would that be resonance with your above ground structure. So there's some potential problems with the peak parameters. With that, there will be a little bit more effort we talk about later other available parameters to better describe our earthquake events. So that's another fact is earthquake magnitudes also matters. So the earthquake magnitudes will give you different type of floating earthquakes. More likely, larger amplitudes of earthquake events will give you earthquake records of longer durations. So the durations is sort of correlate with the earthquake magnitudes. For example, you have a magnitude of 6.5 versus a magnitude of 4.6, and the magnitude for 4.6 earthquake, it died down pretty quick. And in fact, if you look at those two records, you need to realize that there's a lot of different frequency content, and also there's also like the time aspect of earthquake ground motions. Because of different record, if an earthquake will give you like a different acceleration time history, and using one point just to represent earthquake motions, and particularly choose one that being interesting, because like if you just look at the PGA, the TS tells you earthquake loading magnitude 4.6, but this one with a less absolutely magnitudes, in fact, just come from a larger earthquake magnitude earthquakes. So in order to keep track with or capture all those like variability in frequency and also in the time aspect of earthquake loadings, there's other like a earthquake intensity, what we call intensity measure, IM. So it's very popular in structural engineering too. So this is intensity measure. So the intensity measure will try to do a little bit better jobs than just using the PGA 1 point to describe the earthquake loadings. For example, the area's intensity is one kind of intensity measure. It is you take account into both x and y directions of shear wave loading. So pretty much what you do is you take two records. So you take like the x and y measurements of earthquake loadings into account, and you do the integrations. So pretty much the square of the motion. So the square of the earthquake loading, pretty much like by doing it, you will take account of both positive and negative pulses, the amplitudes, and then you do your integrations, and then also you consider the both x and y directions, but each of them normalized by the g. So end up you get interpretations of a dimension, kind of like a dimensionless parameters, and that is your area's intensity. So the nice thing about this is it account for the entire acceleration time history, not just the peak. So there's another like a parameters called cumulative absolute velocity, CAV. So CAV 5 here means like very similar to area's intensity. What you will do is you will take the acceleration time history and then do the integration. So this time we are not squaring it, we just like integrate it. The area's intensity is not dimensionless. Both of them is have the units of accelerations, because you have a square here, and you normalize by the g. So end up you still have the accelerations, same as the CAV. You pretty much just take the absolute values of the acceleration time history and then do the integrations. But the 5 here now is a threshold. It's a threshold that try to cut off the small loading pulses. So so the philosophy here is you assume the small pulses which have an amplitude less than 5 centimeters per second. They assume those small amplitudes loading less than 5 right there. It has no contributions on the overall intensity. So that's why if you do the math according to these equations, pretty much you just take account on the acceleration after you have do the absolute value that is greater than 5 centimeters per second. So that is that's apply a small vessels to remove the small peaks. So that is the CAV5, and there's also like the parameters of CAV. So CAV is the original one, and the CAV pretty much is just consider the integrations of absolute value of the acceleration time history without the vessels. And in fact, there's this is geotech earthquake engineering. We are still trying to find the right parameters and try to find the right answer. Which one is better? Which one is the best to describe earthquake noding? Is still like very hard to reach final solutions. But like seems like at this point we have seen enough not enough, but like have seen some experimental data either from the field and from the lab or some like earthquake record. CAV, actually CAV, not CAV5, not CAV5, but CAV seems like is at the leading edge, and same as the area's intensity. So both the area's intensity and the CAV are the two that through both laboratories, numericals, and also field data, seems like those are very good candidates to describe earthquake loadings. And that's another kind come from another philosophy from Green. So Green is a professor at Virginia Tech. So pretty much this is a Virginia Tech method. They rather than they focus on acceleration time history, they look at energy demand. So what they would do is they would take the acceleration time history, and then they will do a site response analysis, which we'll talk about later. And then like through the site response analysis, they will obtain the stress strain loading on the soil profiles, and then they do the integrations or summations of the hysteresis loops. So this is the normalized energy, pretty much is the area to talk about the hysteresis loops of a stress strain curve. So all of them you need to do it like with a computer package, or you whether you write your own code or like you do it really quick on Excel. I think Excel is just quite hard to do it already. Maybe too complicated for a spreadsheet. But like if you program it, like you take you integrate all the areas and then of the hysteresis loops, then you get the energy. So that's another approach, but seems like at some point like this was quite popular about 10 to 20 years ago, but I don't see like the NED normalized energy demands like have the strong influence as the other two nowadays. So all those three are very popular IMs. So there's and tons of other IMs like being available. So those are geotech IMs. And if you work on structural engineering disciplines, they will have their own IMs to describe the behavior of structures here. But many times the geotech and structures, they will work side by side, and what we have what kind of intensity we interpret for the soils, we pass it to the structures, and those we call those to be intensity measure. It's integrations of some kind, either acceleration time history or some form of energy. And if you plot out the intensity measures, for example the IA, you will tell you how the loading or how the intensity build up with time, because we are doing the integrations with respect with time. So which is nice. So with the intensity measure, you kind of bring in the time domain, the time factor that the previous like peak parameters that doesn't have. Because if you just use one point to describe the earthquake motions, you are not allowed to consider both the frequency contents and also the time domain. So now the intensity measure, at the end of the day, you still only have one parameter, right? Because after you do all these nice calculations, you still just have one parameters. But which is like at the end of your earthquake time history. But at the end of the day, this one parameters will already capture both the frequency content and also the time domain effects. So this is kind of like the kind of the next generations like intensity of parameters to describe earthquake loadings. In the past, we used a lot of PGA, and in this case, like for simplicity, and for very first step, maybe we still use a lot of PGA to do our engineering work. But bear in mind, in the future, pretty much like an intensity measure is more capable to describe earthquake loadings. So another quick examples on how to do the CAV5 calculations. So either in the lab or in the field record. So is outcrop loading. If you have a sensors at the outcrops or the backwalk level, this is where we get the acceleration time history. And then after we do a site response analysis, then we will have our amplified earthquake ground motions at the ground surface. So after we take this, when we get to module 4, when we get to like a later part of semester, we spend like a lot of time to talk about how to convert earthquake ground motions at the backwalk level to the ground surface levels. That's what we call the site response analysis. So this will involve the response of the soil site, and we will learn how to use the software of deep soil. So that's where we need to do a lot of FFT. It's almost impossible to do by the calculations from here to here by hand. We need to change everything into a frequency content using a fast Fourier transfer FFT, and our computer package like a deep soils will help you to do that. So after we have this acceleration time history, if you want to calculate the the CAV5, then first we take the absolute values, and then we take out the threshold. So pretty much now you will cut off the small pulses, which is less than 5 centimeters per second square, and then we do our integrations. Then we will see how the loading is built up with time. So that is the CAV5. Okay, for the durations part, so the second point we need to look at is the durations of earthquake, and the durations is functions of magnitudes and distance. In the past, there's some very rough estimations on the effect of amplitudes versus durations, and it depends on different sites. So this is from a study back in 1977. Could be a little bit outdated, but I hope they give you a general sense on how the magnitudes will affect the durations both on the soil site and also rock site. And very likely for soil site, since you have the de-amplifications effects, so the durations will be a little bit longer than those on the rock sites. And for liquefaction studies, there's also a simple method or simple procedure to convert the earthquake amplitudes into a number of stress cycles. So for example, if you have an earthquake loading, and based on so this is the accelerations, this is times, and based on the earthquake's magnitudes, it will be turned into equivalence of loading cycles for liquefaction's evaluation. So we'll talk more about that when we get to modules number 5 at the end of the semester. Bracketed durations. So for earthquake record acceleration time history, we realize some of the loading peaks may be very small, and there's maybe no damage or no significant effects. And there's some other a procedure try to better capture the durations, effective durations of an earthquake. So some of the simple method in the early days is they take the thresholds of 0.05 G. So whatever greater than 0.05 G's, it counts. But for those like smaller than that, like we kind of ignore. And if you look at an earthquake record, you realize that the earthquake will build up a little bit at the beginning, and then like the peak, dominant pulses comes, and after that the motions will die down. So applying thresholds like that will help you to turn those to eliminate a lot of like small peaks afterward, because many times we will take the earthquake records to convert that into intensity measure, and if we do integrations, those small peaks, like you add them up, they may compensate 10 to 20% of your loading, and when you also do integrations to get the velocity and also the displacement time history, so this will be add up to be like maybe some effect right there. So applying brackets will helps to clean up some noise that we may want to get rid of. For significant durations, there's other like parameters to use to describe earthquake durations. So at the end of the day, like there's a lot of different like parameters, and at the end of the day, it will be up to the engineer choice how to describe the durations. You could use significant durations, you can use like a bracket durations, or you can just use uncorrected time that you have from earthquake time history. It highly depends on your applications, but you need to be clear to tell your colleagues, could be structural engineers, how to look at the matters of earthquake durations. So a little bit more sophisticated way to look at it is to first of all to change or to do some math to convert the whole acceleration time history in terms of areas intensity. So a couple slides before we talk about this, and after you square the ground motions, and then like you normalize by you times the factor of pi over 2g, and take the integrations, you will see how the loading build up with time. And it only take so there's two choice for significant durations. First is look at the 5 to 95 percentiles, and also maybe the 5 to 75 percentile. So the D5-95 is talk about the time between like a 5 to 95% of your area's intensity. So the I sub A here stands for area's intensity, or you could just consider 5 to 75%. So that is the significant durations. So for durations, and also besides the durations, another important factors in earthquake ground motions is the frequency domain. Remember at the beginning we talked about this like three parts that we need to pay our attentions to. First is the intensity. Second is the durations. Now the third is the frequency domain. So in a frequency domain, in the most simple form, for example, so when I have a harmonic motions here, so you can plot this up easily with MATLAB. So once you have harmonic motions with an amplitude of 1 and a period of 1, which means the frequency here is 1 Hertz. And if you do FFT, if you convert this into a frequency domain, so this is pretty much in time domain. It tells you like with time how does motions change. So this is what the world that we're living in. So we feel very comfortable on seeing a time history. But earthquake engineers, you also need to feel comfortable with the earthquake like the frequency domains too. So a graph like this in frequency domain means this one. We have all the motions at 1 Hertz, so this is the frequency at 1 Hertz with the amplitude. So this is the frequency domain. So if you have something like a random noise with a zero mean, like something like this, and if you convert that into a frequency domain, you will have something like that, which tells you most of the amplitudes, the major amplitude loading happens at about 120 hertz, and also maybe 50 hertz. So with a plot like this, will be kind of like, you filter all the frequency, and you will be easily seeing what is the dominant frequency you're working on. And again, like a frequency means natural period. A dominant period in soils, you don't want it to be synchronized with the electro period of your structure. So frequency domain is very powerful in our applications. So Fourier transfer theory. So any erratic signal can be represented as combinations of summations of sinuses of various amplitudes, frequency, and phase shift. So pretty much like if you have a random motion, something like this, you can decouple into different like sine series like this, with different amplitudes and also with different frequency. And through the FFT, you will represent by a graph like here. So for example, if this random motions have three type of frequency, so you can break it down into three type of frequency, and you will show up at the frequency domain. And the other nice thing about if you work on a frequency domain is you can do the filter. So first of all, if you have motions like this, you change it to frequency domain, you apply a filter, get rid of the high frequency stuff like here maybe, and then after and then you do the inverse FFT, you go back to time domain, then you can smooth out your data. So a lot of like our engineering applications beyond civil engineering, a lot of electrical engineering applications like your cell phone and anything else, they work on the FFT and apply the filter. And if you work in geophysics, that's very like typical work you will do there. You need to apply filter to clean up your signal such that you can interpret it like better later. And we will come back to this like FFT when we talk about site response analysis, because the site response analysis, we need to do a lot of Fourier transfer. And now I want you to know this is available, and I want you to start to think about it, or maybe like do some study on your own on about the frequency domain and also Fourier transfer. So the descript like a Fourier transform is what will help us a lot on how to change digital size earthquake time history into frequency domain with these equations. And again, this is a topic that we will come back when we talk about site response analysis. But now I want you to to start thinking about it. If you can, I highly encourage you to do some study on your own on how these equations, where these equations come from, and how to change from a time domains to a FFT. And we will come back to this. We will talk more about this. Maybe I will do a little bit more demos when we get to modules number 4. But if you're interested, you want to be ahead of the game, feel free to study this topic. At least at this point now, I want you to see the importance of frequency contents for earthquake ground motions, because again, from a highly transient and erratic earthquake motions, you want to sort out the frequency, because you don't want like the worst case scenario is your dominant peak, the most like a matter like waveforms or the pulses of your ground motions is being resonance with your structure. That's you want to stay away from. So here, if you have a certain time history, and if you apply the FFT, if you transfer that into a frequency spectrums like here, so we call this FAS, the Fourier amplitude spectrums. So from earthquake time history, so this is the same earthquake time history that we see at the beginning of this lecture, the Gilroy's ground motions. So after like they convert that in in frequency domain, this is how it looks like. So once you convert that, you can easily to find out the dominant period of the earthquake ground motions. So we have a rock site and also we have a soil site, and very typical is that the lateral period of soils, dominant period of soils, usually is much higher than the rock, because you have the de-amplifications going on. So this is more like a ductile, and this is where brittles type of respond. So you have dominant period have a longer period than the rock site when it comes to soil. So we talk about this dominant period, and there's also other ways to look at this type of period. First, what's called a mean period, because the predominant period can be biased because it's only based on a single amplitude spike. So if we do some simple calculations to take the mean on what you have over here, so pretty much this is considering the frequency of a quarter hertz to 20 hertz. And if we do the simple mean calculation, so this is the amplitudes divided by frequency and then normalize it by the amplitudes, then you pretty much you get a mean period. So you will be better represent your ground motions as a whole if you do the calculated mean. So again, we call this to be the response spectrums. So it will be also a very powerful tools for us to see the frequency. So we talk about the Gilroy site. So this is the Gilroy site data. If we have the response spectrum of that, and if we do our integrations once, then we get the pseudo velocity spectrums, and if we do it one more time, then we get the displacement spectrums. So which tell us at different period how the soil as a structure. So soils means the soil columns responds, and at different return period, and what is your expected velocity, displacement, and accelerations. So this is the same thing as before. We talk about the mean periods, and actually there's other calculations. There's also the average period. I think we kind of touch base on this over here, the average period. But they are similar concept. Is you want to have better or more parameter that can be representable parameters to tell the whole story of your response spectrums. So there's the mean period, there's average period, and also there's the average spectral period. So there all the calculations are there. Which one to use? You'll be make the choice as the civil engineers.